Hey y'all, it's Mr. Boyd, and I'm back at it again today, and we're going to be looking at right triangle trig today and identities. Right triangle trig is exactly what you learned back in geometry, so think SOHCAHTOA. So all we're going to be doing today is looking at that in conjunction with some identities and our reciprocal functions to see some more things that we're able to do now that we're in pre-calculus. So before we get into anything too complex, let's start here. We have to remember about opposite, adjacent, and hypotenuse. In order to do that, you might notice we have some actual problems here because we need that to be a right angle, and then we need to identify where the angle is that we're referencing. So I'm going to call that theta. So then we would need to know the opposite is there, the adjacent is here, and the hypotenuse, of course, that's the long one. Okay, so if we're all good with that, let's go on to things that are hopefully a little bit more interesting. Okay, so with this picture here, what we're going to do is we're just going to remind ourselves really quickly what the 6 basic trig functions are and how to use them. Now they do tell us over here that theta is going to be a, so this is the angle to which we're referring when we talk about opposite, adjacent, hypotenuse. And so I'm going to go pretty quick through this one, y'all. So we are asked to find sine of a. I remember from SOHCAHTOA that's opposite over hypotenuse, so that's 5 over 13. Okay, let's go to cosine. Cosine of a, that's adjacent over hypotenuse, so that's 12 over 13. And then tangent of a, saying SOHCAHTOA, that's opposite over adjacent, so that's 5 over 12. Now, we were asked for 6 functions, not for 3. So we also need to do the reciprocal function. So the reciprocal of sine is, sine goes with cosecant. And so, y'all, it's pretty easy. If we know that they're reciprocal functions, we know it's the exact same fraction, just flipped. So that's all I have to do. Cosine goes with secant, or it's paired with secant. And you know what? I realize I put theta there. I probably should have put a to be consistent. So let's go back and fix that. So make that an a. Secant of a is the flipped version of cosine. So that's 13 over 12. And then tangent is associated with cotangent. And so again, flipped version, that's 12 over 5. All right, so nothing too groundbreaking yet. We haven't really done anything new. That's really just sort of review to make sure we're sort of in the right mindset going forward here today. Okay, something that we haven't talked about yet is going the other direction. So what I mean by that is just now we looked at a picture, we were able to figure out sine, cosine, tangent, secant, cosecant, and cotangent. But what we haven't really done yet is generated a picture from seeing one of those equations. So let's try that. So we're told here that cosecant theta is equal to 3. Now, guys, 3 is not saying that the angle is 3. It's not radians, it's not degrees, it's a ratio. So what we're going to do is we're going to remember that cosecant is associated with sine. So if cosecant is 3, then sine must be 1/3 because they're reciprocal functions. Now remembering that that's opposite and hypotenuse, I'm able to draw a picture. So there's theta, the opposite is 1, and the hypotenuse is 3. Or at least that's the relationship they share. So for example, it might be that that's what the picture looks like, although it's honestly equally likely. I have no way of knowing really. Whoops, redo, that wasn't good. So it is equally likely that it could be 9 and 27, because it may have been that that was simplified down, right? So maybe that they said 27 over 9 was 3 or something like that. So in any event, we've generated the picture, and then we can also figure out how this adjacent side relates using the Pythagorean Theorem. So we'd say, for this example over here, we'd say 1 squared plus x squared equals 3 squared. And that would say 1 plus x squared equals 9. Simplify that down to x squared equals 8. And then we'd need to take a square root of that, and we'd have to remember that 8 is the same as 4 times 2. So what I could do, break that down into 4 times 2, so then it says 2 times the square root of 2. Okay, so just want to make sure that you're aware that when we have something like this, or really any trig equation that's pretty simple like this one, if we're having trouble understanding what it is and we need to try to answer some other question, we can always try to draw out a model of it so we can understand what's going on. Okay, now we're going to get into something that is pretty well brand new that we don't really do very often, and maybe you've never done it before. Okay, we're going to use identities to verify an equation. Now, when we say verify an equation, that's a little bit different than what we've done before. So let's go back to like the first year algebra days and remember questions like this. Okay, and so if you got a question like this and you were asked to solve for x, you probably would have started subtracting things on both sides, adding things on both sides. And what your teacher may or may not have talked a lot about is that the moment you start doing the same thing on both sides like this, you've made an assumption, a logical assumption, that the initial statement was true, that both sides are equal. And so what we're starting out here is with a very different logical assumption. We're not assuming that both sides are true. We're actually checking to see. That's what we mean by verify. We're going to check and see if that's true. So what I've started here with is a basic numerical example so that it'll be easier to understand the concept. Then we'll move into how do we do that with trig with some increasingly challenging examples. So all this means is instead of where in the past we were able to multiply things on both sides, add things on both sides, we have to work on each side independently. So it goes like this. So like I'm allowed to do 2 times 3 and say that's 6. So I'm going to put, and then minus 5 plus 1. And I'm allowed to work on the right side in the same step, but I'm not allowed to kind of mix the two together. So I'm allowed to say 6 minus 4 is 2. And then over here I can keep going and say 6 minus 5 is 1. So that says 1 plus 1 equals 2, and I'm going to simplify it one step further, because 1 plus 1 is 2. And so what I've done is I've taken our initial expression, and I've worked it down to something that is obviously true. And that's how I know that I'm done. So y'all, that's what the logic is for verification, and we're going to build up, in fact, in our next unit, we're going to do a whole lesson on how to verify more demanding trig exercises. But this is just kind of our intro today. So let's look at the next one. The next one might be a little bit harder at first, or might feel a little more challenging. Because in our first example, you say, well, I know that I can do 2 times 3. That's pretty obvious. So what may not be obvious to you yet is when you have something like this with sine and cosecant, that you're able to rewrite it like this. We can remember that cosecant is 1 over sine. And I'm going to leave the right side alone. I don't know how to simplify 1. And so now looking at this, I have sine multiplied by 1 divided by sine. I'm both multiplying and dividing by sine, so those can cancel, and I get 1 equals 1. Something that's clearly true. Okay, so logically that's the same as what we started with. And then let's get down here and do one that's even a little bit more exciting. One thing we might want to talk about at first, though, is what the heck is that? Because that may be brand new to some of you, the fact that there's a 2 sitting right there. So guys, here's what I would like you to know, and this works for any of the trig functions. Okay, if I have sine squared of an angle, it doesn't matter, here they're using beta, it makes no difference. That's the same as sine of the angle squared, or if you prefer, sine of the angle multiplied by sine of the angle. Okay, and I'm not even doing steps here. I'm just writing different things that are all the same thing. Okay, I think it's probably pretty intuitive for you to understand these next two. For a lot of people, when they haven't seen it before, this first part can be kind of confusing. So keep this in mind as we go through this question. Okay, we're going to use that same trick that we used on the previous question. We're going to try to express everything in terms of sine and cosine. So here I go. I have sine of beta, cosine of beta, and then for tangent, I'm going to remember that that's sine over cosine. And then I'm just going to rewrite the right side because I'm not sure that I see what to do quite yet. Okay, so sine squared of beta. And then we're going to see, does anything cancel? Well, I have cosine of beta multiplied by sine of beta divided by cosine. So I have cosine divided by cosine. So those two cancel out. And so what I have now is sine of beta times sine of beta on the left. And you know what? I remember that this thing means sine times sine. So I'm going to change the way this is written right here and write it as sine of beta times sine of beta. And so now we've worked down from something that looks challenging to something that is obviously true because both sides say the same thing. Okay, so guys, that's our first basic strategy when we're verifying trig identities, is not always, but often it's helpful if we express the question only in terms of sine and tangent. Now, conversely, as a teacher, that's one of the things that I do to try to challenge you, okay? I'm going to write questions like these that have things like cosecant, tangent, secant, and cotangent in them, okay? To see if we can try to trick you with that. So don't be tricked by that. Now, to add on another tool that would be helpful in solving questions that are more challenging, we have something called the Pythagorean Identities. Okay, and so guys, here's where that comes from. We know that the Pythagorean Theorem is a squared plus b squared equals c squared. Or in this case, let's apply it to this triangle. So we would have x squared plus y squared equals 1 squared. And we probably know that 1 squared is just 1. So here's what we're going to do with that with trig. We're going to remember that another way of understanding x is a cosine value. So we get cosine squared x plus, and we remember that y is a sine value, plus sine squared x equals 1 squared is 1. So all I've done is I've made substitutions here. X for cosine, y squared becomes sine, and 1 squared is still 1. Okay, this is our first Pythagorean identity. Now you can do things like subtract cosine squared on both sides, or subtract sine squared on both sides, or subtract both of them if you like. Okay, it doesn't really matter. We can manipulate it because it's something that we now, because we derived it, we know that it's true. Now, a lot of teachers will have you memorize 3 or more Pythagorean identities. Guys, truthfully, there's really only one. There's many different ways of writing, and we probably write this in 10 or 12 different ways. I'm going to show you what other teachers would mean when they're making you multiply 3 of them, just so you can understand what those are, because we will need to use other forms of this. So imagine there was a question where we needed to use cosecant squared for something, okay, or cosecant x or cosecant theta. In fact, you know what, just to not be confusing, I think I am going to come back and change these to thetas, because otherwise it might seem like we're using x. So theta. Okay, so maybe there's a question that used cosecant theta, but we say, wait a minute, but this doesn't use cosecant theta. This uses cosine and sine. Well, what we could remember is that cosecant is the same as 1 over sine, and we say, hey, you know what? I could, since this is something that is true, I could multiply or divide by the same thing on both sides. I could divide this side by sine squared theta. Now, if I did that, I would need to do it on both sides. Okay, now, before I get any further, I'm going to put a box around this little guy right here, because this is our main Pythagorean identity. This is the one that you really do need to know or memorize. You can always derive the others if you forget them. That's when you really do need to know, though, and I want to make sure you understand that that's what we're getting at here. It's not just a bunch of steps. That's the one that you really have to have. Okay, let's talk about how to simplify this now. 1 over sine squared turns into cosecant squared. Okay, we have sine squared over sine squared, so that's 1. And we have cosine squared over sine squared, so now we have cotangent squared there. So this is another Pythagorean identity. Now, some people will, or teachers or some people say, hey, that's one of them, that's a different one. Guys, I hope you can see it's not different. We did one step. It's really still the same stuff. We just changed the way it looks. Okay, and so there's one other way to do it as well, and so I'm just going to derive that one here while we're thinking about it. So I'm going to start with cosine squared theta plus sine squared theta equals 1. And then what we're going to do on this one, we're going to divide both sides by cosine and see what happens, or cosine squared. So cosine squared theta, and then let's simplify it. So over here, cosine squared divided by cosine squared is 1. Sine squared over cosine is tangent squared. And 1 over cosine is secant squared. Okay, and so this is our, what a lot of people would say is our third one. I contend they're all equivalent, but they are useful for different things. Okay, so we can think about them as different if we want to. So what do we have now? We have Pythagorean identities that cover cosine, sine, cotangent, cosecant, tangent squared, and secant squared. We've covered all 6 of our basic functions. So now that we have these identities, let's try to answer a question that would be made easier by knowing them. When we look at a question like this one thing I want you to keep in mind is that often you're not going to be able to just look at it and see what to do. Okay, that's really, really normal. What I want you to think about this is, in terms of your mindset, is that basically we have a puzzle in front of us, and we have some building blocks and some puzzle pieces from the Pythagorean identities, and we're just going to play with them and see how the blocks fit together. And it may be 2 or 3 steps until you find out something that works, or until you find out that your strategy doesn't work. So be open-minded about that and be willing to sort of persevere when it gets difficult, okay? One thing that jumps out at me right away in looking at this is that on the left side I have cosines, and on the right side I don't. So my approach to this, I either probably want to try to get rid of the cosine, or I want to try to introduce a sine over here. So since I'm dealing with sines and cosines, one thing that was helpful to me when I was learning how to do these is I would write out the Pythagorean identity that I think will be helpful. So I think that's probably, cosine squared, and I'll use beta on this one because that's what's in the question, plus sine squared beta equals 1. Okay, so, and then what I'm going to try to do on this one, and there's lots of right ways to do this, but the easy substitution that I'm seeing at the moment is I could get rid of that 1 because I'm noticing this side doesn't have a 1, and by doing so, and turning 1 into cosine squared plus sine squared, I'm actually introducing a cosine squared into the question. So I'm going to leave the left side alone. I'm not going to change anything right now. And then instead of 1, I'm going to write this whole chunk. So cosine squared beta plus sine squared beta minus 2 sine squared beta. Now, guys, it's really tempting to do something like minus cosine b on both sides, but remember, we're verifying, which means you're going to work on each side of the equation independently. What I do notice is over here, we can actually simplify, because we have sine squared minus 2 sine squared. That becomes negative sine squared beta, and that's really good news, because that's what we have right here and right there. That's great. And then what do I have here? I still have a cosine squared beta. I think I'm going to rewrite the left side now. So cosine squared beta minus sine squared beta. And hey, look at that. It's done. These two sides say the exact same thing, so that's something that clearly is true. Now, the other thing I want you to keep in mind on this is when you go to check your answers in the back of the book, or when you do a question and it's graded, we are not grading your answer, because people could come to totally different answers. Like, they could have subbed out the cosine beta instead of the 1. That would have been fine. And you'll get a different line at the end. What we're looking at is, was your logical process as you went through this problem a valid one? We're not looking at this final line. That's not the answer. The whole thing is the answer. And that's a little bit different than what we normally do. So please be aware of that. Okay, we've been switching gears a lot today, and so we're actually just going to keep doing that right now, guys. We got these 3 questions right here. We're kind of doing trig functions of any angle at the moment. So we want to try to find theta such that each of these is true. So for some people that can be a little bit hard to think about, but what we could remember about sine is that it's a y value. And so what this first question is really asking, it's asking where on the unit circle, that's what theta means, where on the unit circle is the y value 1? Well, let's think about that. Y value is probably 1 right there. That's at pi over 2. So the solution to this one is theta equals pi over 2. That's all it is. What about this next one? They say cosine, so I'm going to make a note. They're talking about an x value. They want to know where on the unit circle is the x value negative root 3 over 2. Now, guys, for the first time today, I'm going to suggest you pause the video and try this one. I really think you could probably get this on your own, so give it a shot. Okay, here it is. It's an x value. It's negative, so it's going to the left. And that's going to be this location here and that location there, and I believe that that is 5 pi over 6 and 7 pi over 6. So notice they said find all theta. Sometimes there's more than one. What about cotangent? All right, we got to remember that cotangent is x divided by y, and they're saying that it's 1. So if we have a fraction that equals 1, that would tell us the 2 values are the same. And I can only think of 2 places on the unit circle where the x and the y value are the same. You've got one right here because both x and y values are root 2 over 2. That location is at pi over 4. So that's one of the answers. And then the other one's right down here where both coordinates are negative root 2 over 2. And that one is at 5 pi over 4. We're now going to look at the same type of question, just that involves a little bit more advanced thinking, more than just recognizing values on the unit circle. Okay, so for this one, let's try to find something we can relate it to that we already understand. Okay, yes, we're finding the third quadrant value. I'm going to make a quick note. Third quadrant is down here, so it's something down here, and we're finding theta still, so very similar to what we worked on just a moment ago. But this looks a little bit more challenging, because I want to relate it to something that you understand well already. If I gave you this equation, that's meant to be a parenthesis. Okay, and I say, there's the equation, what are the values that make that true? I'm guessing that most of you can probably look at that and just spit out those values as answers. Okay, we talked about that a lot in our second unit with quadrilaterals. So how would we deal with that same thing here? Notice you have a chunk of math equals 0, a chunk of math, you have 2 things here multiplied together and they equal to 0. So either sine theta plus cosine theta equals 0, or sine theta minus cosine theta equals 0. Those are the 2 possibilities. So let's work on each of those independently. I'm going to modify these just a little bit. One way of thinking about this, by subtracting cosine to the other side, I could think that this is saying sine theta equals negative cosine theta. Or, put a different way, we're looking for spots on the unit circle where the y value is equal to the opposite of the cosine value. And so can I think of any place in quadrant 3 that does that? Okay, up here when we're talking about pi over 6, the values aren't equal. And down here when we're talking about 4 pi over 3, the x and the y values are not the same. In the middle, I've got root 2 over 2, or excuse me, negative root 2 over 2 and negative root 2 over 2, but they're not opposites. So there actually is no third quadrant solution to that. So now I'm going to look at the other one. Doing the same modification over here, I get sine equals cosine. Now remember, all that's saying, we're looking for a place in quadrant 3 where the y value and the x value are equal. And I believe that's right here because the coordinates at that point are negative root 2 over 2 and negative root 2 over 2. And that seems to fit the bill of sine being equal to cosine. So now we have to figure out how many radians is that. Well, that's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and that's 5 pi over 4. Okay, so this is the first question that's starting to incorporate sort of our learning from factoring from previous units into our new learning about trigonometry. So all that stuff is going to start to come together here for us. And then we're going to think about one more thing in this sort of scattered video today where we're jumping from topic to topic. But that's this one here. And notice I'm asking you what's x, but I'm saying you're not going to use a calculator on this one. You might want to pause the video and think about this. I think you could probably figure it out. Let's see if you can. What I'd want you to do here is relate this to the unit circle. And so knowing that's a 30-degree angle, we're talking about this spot right here. And so we know that normally on the unit circle, this length is 1/2, and this length is root 3 over 2, and this length is 1. And so we're looking at basically the same triangle here. It's just been scaled up, okay? But all the proportions between the side lengths are going to hold. So this is 1/2. This is an 8, which tells me this triangle is 16 times bigger. So all I'm going to do down here for x, we're going to remember that, yeah, the proportion is 1/2 root 3 over 2. That's how we knew it was multiplying by 16. So this thing down here is root 3 over 2, but it got multiplied by 16 the same way this did. 16 over 2 is 8, so this side length is 8 root 3. Okay. That's going to be all for today's video. Hopefully you enjoyed it, and we'll see you next time.